Hello class, this is lesson 7-4 titled How to Use Similar Right Triangles. There's a lot in this lesson, so just try to keep up. Theorem 7.5 says the following. If the altitude is drawn to the hypotenuse of a right triangle, okay, and it's from the right angle, then the two triangles formed are similar to the original triangle and each other. So I kind of left this big black triangle and then I drew the other two triangles that are created when this altitude is drawn straight from the right angle. Okay. So let's just write some things that are similar then. So I can say that triangle ABC is similar to triangle ACD. So if I was going to redraw the black triangle, I would match up the points that were similar to the one in the blue triangle. Also, I could see that triangle ABC is similar to triangle CBD. It's really important to know the order of all of these. And furthermore, triangle CBD is similar to triangle ACD. Oops, I need an A in there. Triangle ACD. So this will probably be more evident in our next example. So let's just go ahead and show it to you. So in this example, we're supposed to identify the similar triangles, and then it wants us to find this missing piece right here, X. So at the beginning, you're only given this one diagram. And for me, I always think it's helpful just to redraw stuff so that I really understand what is going on in every situation. So I'm going to go ahead and do that. I'm going to redraw this diagram. So I'm going to draw the large triangle first and label its points R, S, and T. T is where we have the right angle. Okay. I'm also going to label any of the sides of this triangle that I know. I know from R to S it's 165 inches. I also know from R to T that it's 152 inches. And I furthermore know that from S to T it is 64 inches. So at least for the large triangle, I know all three sides. Then when I'm going to just draw this other half kind of the triangle, I need to flip it around and look to see, well, where the right triangle is, or where the right angle is, that is the point M, and the point down here is still R, and it's going up to T. Okay, so I just want to make sure that I draw them in the correct order. Do I know any of the lengths? Well, from R to T, that's 152. And the only other thing that I know is from M to T, it's labeled as X. I don't know R to M, so I'm just going to leave that alone. And then the final one is this very small triangle, which is this section right here. And I'm looking for where the right angle is, and again, that's at M. And it's going up to S and down to T. So T is going to be that smaller angle. And the things that I know from S to T that that is 64, and I also know from M to T that that is X. Okay, so I have these labeled. So let's just do the first part where it's asking us to identify the similar triangles. So I can just state these triangles. Now that they're all drawn in the same fashion, I can say that triangle RST is similar to triangle RTM, which is also similar to triangle TSM. So that's our first part. So now we just need to find what X is. And so having them drawn in the same fashion is going to help me relate one missing side to three known sides. So what I'm going to do is I'm just going to relate this triangle in the middle to the first triangle, because I can see that TM will relate to ST. So TM to ST, and that should be equal, since they're similar, to the ratio of RT to RS, the hypotenuse of both of those triangles. So TM is our x, ST is 64, RT is 152, and RS is 165. And when I do cross multiplying, I'm going to get 165x is equal to 9,728. And when I divide, I'm going to get this really long number. It's going to be 58.957575. Keep on going. So I'm just going to say it's really close to 59 inches. And that's going to be my answer. Okay? So as I said, we have a lot to cover. So let's move on to our next part. Going back to that triangle that I drew at the beginning, if I drew where I kind of color-coded some of the sides and the altitude, and if I was going to redraw based on these color-coded sides, the first triangle that I would draw would be this smallest one, the CBD. And so if I redrew it, then this is how it would look. If I redrew the second one, which would be ACD, the one with the kind of greenish and the red side, then it would look like this. And then if I redrew the very large triangle, ABC, it would look like this right here. Okay? So what's really cool is that there's something in geometry called geometric means. And it's basically they found some really cool ways to relate specific sides in all these triangles based on these color coordinating things, where they realized, oh, the base of this large triangle is the same as the hypotenuse in that triangle, or the shorter leg of this triangle is the same as the hypotenuse of the smaller triangle. And they were able to set up some proportions. So these are called the geometric means proportions. So the first one is comparing the short legs of 1 and 2. Okay, so I kind of labeled my triangles up there. So the short leg in triangle 1 is BD. Do you see that right here? BD. And the short leg of triangle 2 is CD. Well, they found that that is equal to the long legs of 1 and 2. So the long leg of number 1 is CD, and the long leg of triangle 2 is AD. So look at that. If I just have 3 pieces of information, I can figure out what the fourth one would be. Obviously, CD is the same in both of them, so it's kind of cool. The next one that we're going to look at, let me move this up, is the hypotenuse of 3 and 1, and then also the short legs of 3 and 1. So looking back to the top, the hypotenuse of 3 is AB, and the hypotenuse of 1 is CB. And this is equal to the short leg of number 3, so that would be BC, or CB again, and the short leg of 1, which would be BD. Kind of cool. See how we have CB in both of those? So then the final one is the hypotenuse of 3 and 2, and also the long legs of 3 and 2. So I'm going to leave a little bit of room so that you can still kind of see that right there. So the hypotenuse of 3 is AB, and the hypotenuse of 2 is AC. Then the long leg of 3 is AC, and the long leg of number 2 is AD. So look at that. It's kind of cool. I'll move it up so that you can see it. So based on these, we have a couple of theorems that are going to help us out with organizing some of our thoughts and just realizing different geometric means with different parts of triangles. So here is our first one. It is theorem 7.6, and let me move that down. There you go. And it's called the geometric mean or altitude theorem. And it says, in a right triangle, the altitude, okay, the altitude is right here from C to D, from the right angle to the hypotenuse, is going to divide the hypotenuse into two segments. That's just kind of given. It's not telling us anything specific. It's just saying that this is splitting it up into two different parts. But the cool thing is that this altitude right here is going to be the geometric mean, so something that's going to be the same when you're comparing the lengths of these two segments of the hypotenuse. So what it says is that, let's say this length right here, BD, which is one of the shorter legs, compared to CD, which would be the short leg of this triangle right here, is going to be the same as CD compared to AD. Okay, so this right here, the CD, is the altitude, and it's the geometric mean of the two segments on the bottom, the AD and the DB. Pretty cool. I'm going to keep this diagram to help us out with this other theorem, 7.7, so maybe I should move it down so you can still see it. And what it says is, it's the geometric mean leg theorem. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. So same thing that was stated in the theorem above, but now it's saying that the length of each leg, okay, is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to that leg. Okay, so let's just start with one of the legs. So let's say how CB is one of the legs. Okay, well, I'm going to write that CB is going to be on the bottom and CB is going to be on the top here. Okay, this is where the geometric mean is, that leg is going to be on the bottom for one of the ratios and on the top for another ratio. Well, CB relates to AB because CB is the hypotenuse of this very small triangle, and then AB is the hypotenuse of this large triangle. Well, in the large triangle, CB is also the shorter leg, so in this small one, let's see here, DB is the shorter leg there as well. Okay. The third one that we're going to write is AB to AC. Okay. So this time AC is going to be our geometric mean. It's the longer leg, and it's going to be up here on top. And that's going to relate to AD. Okay, so AB, again, is the hypotenuse compared to now AC, which is the hypotenuse of this medium triangle. And then looking at the larger triangle, AC is the longer leg compared to AD, which is the longer leg of that medium triangle as well. Okay, I know it's confusing, but if you just have this down in your notes, it's really going to help you out. And let me show you why. We're going to end with this example right here. Find the value of y using geometric means. Okay, so what I'm looking for is to figure out what y is. And since I only have three things labeled, I can figure out, okay, this right here, this y, which one of the geometric means would I be able to use for the ratio? Well, it was the one that was comparing the hypotenuse and the short leg. Okay, so I'm going to write that down. Hypotenuse compared to the short leg. Because looking in this big triangle, I have the hypotenuse and I have the short leg, and looking at this small triangle, I also have the hypotenuse and the short leg. So that's what you're going to compare. So let's see here. If I want to have the y on the top and on the bottom, because y is the hypotenuse for the small one, then 9 is the hypotenuse for the big one. And if y is the short leg for the big one, then 3 is the short leg for the smaller one. Okay, now it's a little confusing because you have two y's, but let's go ahead and multiply. Y squared is what we're going to get, equal to 27. And then when we take the square root of both sides, we're going to find that y is equal to, well, this is 9 times 3, and the square root of 9 is 3. So our final answer is going to be 3, or radical 3. Okay? So this may have been confusing for you, I know. Just hang in there. We're going to answer all your questions when we get to class, and I will see you then.